Determine the unique value of z so that log base 6 of z plus log base 36 of 3 is equal to 2. Now, why did I say there? Well, logarithms, when I see logarithms and I see, oh, there's an addition to logarithms, what I want to do is combine them. Right? Typically, you want to combine things, make them simpler. But the problem is my property, my rule for, or my law, whatever you want to call it, for logarithms, you can only add them if the base is the same. Well, we don't have the same base. We got 6 and we got 36. So we can't just combine these. If you're in a rush, you're going to say, oh, 2 is equal to log base 6 of 3z. You can't do that. So I need to find a way to combine these in a useful way. Now, something that does catch my eye, 36 is a power of 6. When you try and simplify or work with logarithms, you want to be thinking in terms of powers. So for a moment, we're just going to call timeout. I just want to look at log base 36 of 6. Okay? What we might try and do is say, okay, well, 36 is a power of 6. How about we use the change of base formula to rewrite this? Now, unfortunately, 3 is not a power of 6, but it might be worth it. Log base 6 of 36, 6 to what power gives me 36? 2. Right? 36 is 6 squared, and then the log base 6 and the 6 cancel out. So this is really log base 6 of 3 all over 2. Now that's nice because it does give me log base 6 that I can work with my other log base 6. So far we have log base 6 of z, and now we have sort of a half, or divide by 2, log base 6 of 3. Now I like these log base 6s because I can add them, but oops, there's this 1/2 here. What can we do? Well, we have another logarithm property. I'm going to write it over here that says log of a power is the same as having the exponent, or the power, out front. So what we can do is we can say, well, we've got a half. How about we bring it inside? And so we can rewrite this log base 6 of z plus log base 6 of 3 to the 1/2. 3 to the 1/2, by the way, we can write as square root 3. Because we know exponent, 3 to the 1/2 is the same as root 3, square root of 3. And now, oh great, we have 2 logarithms of the same base. We can finally combine them. Just have to multiply the insides. So root 3z, log base 6 of root 3z, and we're told that that's equal to 2. Okay, great. How do I solve for z? All right, how do I solve for z? Well, we don't need an extra piece of paper. We can just continue up here. Well, I've got a single instance of my variable. How do you cancel out log base 6? Do 6 to the power of. Introduce a base of 6. 6, log base 6 cancel, you get root 3z, and then 6 squared is 36. And so z is going to be 36 over root 3. There we go. There's a final answer. That's exact. Now, some people will say, yeah, but I don't like having square roots on the bottom. Personally, I don't really mind, but I do know that plenty of people don't like doing that. So one thing you might choose to do is say, well, 36 is 3 times 12, and 3 is just the square root of 3 squared, because the square and the square root cancel out. Square root of 3 squared, well, that's just 2 root 3s. And now one of them can cancel on the bottom. So maybe a nicer looking answer might be z is 12 root 3. All right, that's also perfectly acceptable. I would say it certainly looks prettier, but they both mean the same thing. If you were to grab a calculator and calculate them, you'd get the same thing. But yeah, I know some people don't like roots or radicals in the denominator if they can help it. But there we go.